All right. So yeah, thank you everyone. So today I will be talking about understanding the principles of large language model. That was the topic I was given. So first I will start with the progress of language technology that we all know in English language. For example, we know since 2022, a new model was released called ChatGPT that you can chat with. And then you can ask different queries. For example, I asked this query, who brought Ebola disease to Nigeria?
Are you using audio?
And here you have like an answer, which is good in English. I'm hearing some background noise. Should I continue or wait? Hello? Hello? Should I wait or continue?
No, no sound. I guess this is down. Actually, this is down. Let's do that. This. Maybe we should unmute. Maybe I'll go down there.
Hello, Dr. Adelani.
Yeah,
Can you hear me?
I can hear you.
Oh, so sorry. They are trying to restore the sound at the main hall. That is why. Please, I'm so sorry. So
Can you
it
hear
shouldn't be
us now?
restored.
Can you hear us?
Sorry.
All right, let me start again. So today I'm talking about understanding the principles of large language model. Um, so I started off by talking about this technology called ChatGPT, which is an example of a large language model. And you can query and ask a question like, who brought Ebola disease to Nigeria, where you have a very detailed answer. But if you ask the same question in other languages, other Nigerian languages like Yoruba, if you speak this language, you would know that actually the um, prediction is not correct. And because the prediction is not correct, that means the answer retrieval is worse in another language like Yoruba compared to English. But if you do the translation, I think the translation seems to convey the right information, which means like a technology like ChatGPT, although it's very powerful in English, actually doesn't work very well in many languages. Apart from that, LLM abilities extends to math and code. So you can ask a question in math, like Josh decides to flip in a house. He buys a house for $80,000 and then puts it in $50,000 in repairs. This increased the value of the house by 150%. How much profit did he make? So this is an example of what you can ask um, with like ChatGPT. And the model breaks down the solution to you that if you already, the value of the house was initially 80,000, and then he has repaired it, then that's 130,000. And after it kind of increased, the value of the house increased by or 50,000. So that means um, that means the value of the house will now increase to something like 200,000. And then you can calculate how much profit it makes when you say 200,000 minus uh, 80 80,000 minus 50,000, and that is like 70,000. And this is what is called chain of thought reasoning, where the language model actually breaks down the solution to the task. And this has been known to actually improve performance. Apart from that, if you, of course, if you say ignore chain of thought and you said answer the question in a concise way, the language model is also able to give you the answer without explanation. Okay, so, but you can also use this to generate code. For example, you can say, write a code to generate a Fibonacci sequence in Python, and it's also able to generate the code for you. You can also use this for correcting your code, for debugging and all that. It's not always reliable, but it's improving day by day. The good thing in natural language processing is that almost all tasks in NLP can be converted actually into this slow, closed style where you can prompt the language model. So whether you have text classification or token classification or tagging, text generation, you can use the language model for almost any task in NLP, including regression tasks. So prior to transformer, what we need is prior to transformer that backs. So transformer is a technology that actually power all this language model, and it was released in 2017. Oftentimes, we need large amounts of data, which are not always available um, uh, for many languages and domains. And even prior to that, you often require if you use smaller models like naive-based, you require a large amount of data and you need to do a lot of feature engineering to achieve better accuracy. But currently, we don't need to do a lot of feature engineering if you compare to classical NLP methods. With deep learning approach, you can actually do better than the classical NLP approach. And LLM is an example of a deep learning approach to actually solving many classification tasks. So before 2018, these kind of models like classical NLP models are very popular, like naive-based. But starting from 2018, what we do is what is called self-supervised pre-training. You can train on a large amount of text data on the web, and then you can actually develop a very good encoder model, like a BERT model, which you can now fine-tune on labeled examples. If you're able to use this kind of framework like BERT, T5, you will be able to actually achieve very good performance on downstream tasks. However, but these are often require some labeled example, like maybe 100 or 1,000 instances. But today, we also have a new branch of models called the decoder-only models, starting from GPT-3 that was very successful. And this kind of decoder-only model doesn't require a lot of examples. Actually, you can just prompt it with few examples, like 5 examples, or even 1 example, or no example at all, and it will give you a very good performance. And all these are also based on transform architecture. So in the previous paradigm, we call this pre-train fine-tune paradigm, and now we call it pre-train, prompt, and predict paradigm. So where you can pre-train a model, and then you prompt the model to predict, and then you need a verbalizer to extract what was the result of the prompt and extract it out. So the basic idea of language model is to actually estimate the probability of a text corpus. Given a text corpus, what is the probability of the text? Or you can view it as what is the probability of predicting the next word given the context. So if you say if you have like an example, like the cat is sitting on the mat, and then the context is the cat is sitting on, and then you want to predict mat. So this is a very quick, like a very simplistic definition of language model. And what we do nowadays is that we want to learn a parameter that can actually learn this probability of predicting the next word given the previous keywords. So, of course, we have different kinds of language model. We have the encoder-only model, we have the encoder-decoder model, and we have the decoder-only model. So first, I will start with the encoder-only model just because of time. I'm kind of a little bit in a rush. So for the encoder-only model, a very good example is BERT. And the idea is that you want to predict not the last word. You want to not to predict the next word, but you want to predict a word in between. So if you have something like Berlin is the dash of Germany. So it's a mask of Germany. So you want to predict what is the missing token there. And once you have marks like that, this is how the BERT model was portrayed. Another objective that it was portrayed on, which is no longer used again, is what is called next sentence prediction. So you want to predict if the model can predict the next sentence with high accuracy. So if you have two sentences like dogs are friendly, malaria is deadly, these sentences are not related and they are not likely to be in the same document. So the next sentence prediction will be 0. If the next sentence prediction, if you have something like dogs are friendly and cats are friendly, then this is probably going to have a next sentence prediction of 1 because those two sentences can co-occur in the same text. So, and if you're able to train your model using these two objectives of pre-training task, you can be able to fine tune it on a downstream task like question answering, like squad, name entity recognition, or other tasks like natural language inference or sentiment classification or any other task. But this requires you to have available fine tuning data. So, BERT has established like strong baselines on many tasks. As you can see, actually, when the paper was published, it was the best model on the glue benchmark, as you can see. For Cola, it's actually improved from 35 to 60.5. Apart from that, we also have other models that try to improve over BERT, like Roberta, which actually increased the pre-training data from 16 gig to 160 gig. And also they remove what is called the next sentence prediction that is no longer necessary, and then you will still be able to achieve impressive performance. And we also have other extensions of this like SLNet, any Herbert, Electra. Electra is quite interesting because instead of trying to predict the missing token, they actually use something like what is called a generative adversarial network, where you have a generator and a discriminator. And they replace the objective by what is called replace token detection. Instead of saying predicting the missing token, you want a classifier, which is called a discriminator, to know if to actually detect if a token has been replaced instead of predicting the mass token. Apart from that, we have different multilingual models. You can use this in English, and then you can even use it in many other languages. So the early version of multilingual BERT only support 3 African languages, and XLM Roberta supports 7, and RenBERT supports 11. And so they do not support a lot of African languages, for example. For example, like multilingual BERT only supports Yoruba as the only Nigerian language, while XLM Roberta supports Hausa. It doesn't support the other 2 Nigerian languages. But there's a simple way we can actually extend this capability of this language model to many languages. But before that, another interesting thing is that you can distill this model. Most of these models, initially when they were trained, were a bit too big. And there's a way you can distill it so that you can have a smaller model called knowledge distillation. So you can have MBERT with 170 million parameter, and then you distill it to something smaller, and also like SLMR to something smaller. So if you want to adapt your mass language model to a new languages, for example, the languages of Africa that are not covered, I told you that XLMR only support like Hausa language in Nigeria. What if you want to extend it to Igbo, Yoruba, and other languages? So a simple approach we develop is actually using what is called just multilingual adaptive fine-tuning, where you can take the initial encoder and then you adapt it to other languages. And by this, we're able to extend the capability of this model to 17 most resourced African languages, including the 3 big Nigerian languages, Hausa, Igbo, Yoruba. And then we're able to cover many regions in Africa with a very good representation model. All right, so another kind of model that is popular is the T5 model, which is based on encoder-decoder architecture. And the idea is that every task can be casted as a text generation task. So in the BERT model, we are just predicting the max token. Here, we want to be able to use the same model for any task. And this is the idea of T5. That if you give it a translation task, give it a text generation task, give it a sentiment classification task, it should be able to give you the answer. And this is also based on T5. And actually, T5 is the only model that is using the two sides of the transformer architecture, both the encoder side and the decoder side. For the BERT model, they only make use of the encoder side, while for the GPT model, they only make use of the decoder style. So for the encoder model, one thing is that they train on a huge amount of text, 750 gigabytes. I told you that BERT model was trained initially on 16 gigabytes of text. Roberta was trained on 160 gigabytes of text, and T5 was trained on much more data, and also has different versions from its T5 small 60 million parameters to 11 billion parameters T5. And then it was trained on an objective to actually not predict the missed token, but actually it's also trying to predict the missed token, but it's trying to generate the entire text. So basically you have an input like thank you mask to mask week. So you have two mask tokens, Y and X and Y. So, but what it's trying to predict is trying to reconstruct the entire text by predicting what is missing in X and what is missing in Y, so that you'll be able to read the full sentence as thank you for inviting me to your party last week. So basically, you're trying to reconstruct the entire text. This is the way T5 was trained. So apart from that, we have the GPT model, which is the third branch of models. And the idea was that the first initial GPT model was trained on just 1 gigabyte of text. And the objective is like very simple language model. If you have the chicken lays and dash, this was the way it was trained. And it's going to predict what is the next token, which is the egg in this case. So apart from that, the authors also showed that you can also use this very similar to the BERT architecture. So where you can just attach a classification edge on top, and then you can use it for different tasks for sentiment classification, multiple choice QA, and so on. But this was actually a proof of concept, and it was trained on very, very little amount of text, 1 gigabyte. So then they have GPT-2, which was actually started gaining more popularity. It was trained on the same objective, but now they train on much more data, like 8 million documents or 40 gigabytes of text. So they moved from 1 gigabyte to 40 gigabytes of text. And they also produce the different models from 117 million parameters to 1.5 billion parameters. So, and then the question is scaling all you need? Because now we move from 1 gigabyte to 40 gigabytes. And then we have version 3, which is GPT-3, and it was trained even on much more data. So GPT-1 was trained on 1 gigabyte, GPT-2 was trained on 40 gigabytes, GPT-3 was trained on 570 gigabytes of text. And then they also have different versions, but actually the most popular one is the latest version, 175 billion parameters. And the answer is that, okay, if you really scale this language model objective, you can have better performance in general. And then the last thing is that if you compare GPT-3 model to other models, you find out that everybody is scaling, it's increasing the model size, and also this increases the compute you use for training and the data. So the last version is GPT-4o or GPT-4, which is the current models we have. Of course, they have this O1 model that we have no details about. So GPT-4o, what we know is that it will have been trained on even more data than GPT-3, but we have no information about how much data it has been trained on. But there are other questions that GPT-4 was trying to explore. The question the GPT-4o was trying to explore is, okay, how can we make LLM converse like humans? How can we make them to follow instructions? How can we make LLMs safer? So, and then these are questions that were very important to, for example, OpenAI when they were developing this model. But GPT-4o is now a chat-based model that you can chat with, and also became the state of the art over many, many difficult tasks like MMLU, A1 to reasoning challenge, which is like scientific question answering, and also grade school mathematics questions. The question is, how large is a large language model? Because of time, I will give you the answer. I think most of us will agree that if you have a model that is around more than 8 billion model is like a big model. Some people believe like a 1 billion model can also be referred to like a large language model. So most models that are used now often have like minimum of 7 billion parameters. So, but how do you develop a very big, a powerful LLM? You first train on a lot of text, and you can also append a lot of code to it. You train on a lot of annotated data, and then you use human feedback also to improve the model. And then you can also train with additional chart-oriented data. And this was how like a model like ChatGPT was developed. Of course, there are many challenges of this model. One, multilinguality. That means it supports less number of languages. Number two, it's not really factual. Sometimes it gives you a wrong answer that is not actually factual. So use it with caution. And of course, there's hardware restriction because the models are getting bigger and it's difficult to actually use them for many practical applications. And of course, there are other issues like broken evaluation, privacy concern, tokenization issues. So, but the interesting thing is that while developing this, I've told you that ChatGPT is very powerful, but I can also tell you that prompting of a model is not only for decoder-only style of model. You can also build an encoder-decoder model that allows you to prompt the model. For example, TO was developed by constructing many prompted data sets, like for different tasks, like summarization, you create a prompt for summarization, you append an example for it, you create a prompt for sentiment classification, you append several examples for it, and you train a T5 model on a concatenation of all these prompted data sets. And then you may be able, and the resulting model, which is T0, can now be prompted and has very good performance. So, and this has been extended to multilingual setting where you can use a lot of tasks that are available for different NLP tasks, and then you create a prompt for them with examples, and then you can fine-tune this to actually create a more powerful model that can be prompted. So, and this was how a model like Aya, probably you have heard about it, was created, where they fine-tune on a lot of corpus in NLP and a lot of human annotation to actually create a model based on MT5. So, and you can see that this instruction tuning is very effective. And this is from the paper of FLAN-T5. This is a paper from FLAN-T5, and you find out that if you had instruction tuning, you always improve performance. For example, from T5 large to FLAN-T5, there's like 18% improvement in performance. And from T5 SSL to FLAN-T5 XSL, you can improve by almost 26%. So how do you build a powerful language model? Maybe this is where I will stop. And for the most important thing is that if you have trained a model based on labeled text to predict the next word given the context, you also need to collect a lot of demonstration examples, and then you need to build a reward model that will give you feedback so that it's very similar to conversing with human. Basically, it's collecting feedback from human, so human feedback, and then you can optimize this reward model to actually have a stronger model. And this is what was done. You have like a model like GPT-3, and then you align it with human feedback. You have instruct GPT, and then if you align it for safety with safety data sets, you can have a model like ChatGPT. And the last one is evaluating LLMs. And I want to give you an example of how you can evaluate LLMs for news topic classification. So this is an example of news topic classification where you have 5 things to know about Nigeria as a business category. You have a entertainment category. You have a health category. And the question is, how can you use LLM? I'm trying to skip slides. How can you use LLM to predict, actually, to solve this task? You can prompt a language model. So this is an example of the text. You have the headline, you have the text, and then how do you solve it by prompting? So this is an example of a prompt where you can ask, oh, is this piece of news regarding these different categories? You provide the headline, you provide the text, and then it will give you an answer like this. This is a piece of news regarding politics. Okay. And the question is, how do you convert this to actual category? Because the language model doesn't give you the exact category you need. And it can give you different versions, like a single word, an explanation, a sentence describing it. So how can you resolve this? So normally you need to write a verbalizer that can convert this prediction to the category you need. But this is very difficult because you have to write a lot of heuristics and all that. So, and this is an example of a verbalizer that says, once you see finance converted to business, once you see economics converted to business category. Once you see sports converted to sports category. However, one way to standardize it is using a tool called LLM-eval, which actually helps to standardize this. So instead of trying to collect the prediction, you can actually collect the logits. So logits is at the last layer of the language model. So the logits are converted to, you have a probability distribution over the logit that actually now predicts the sentence. So you can analyze this logit and then make predictions like that. So this tool is very powerful, and then you don't need to write a lot of heuristics and verbalizer for your LLM evaluation. And this tool is available. I've provided a link here, and then you can give it a try on different different benchmark. This tool is very, makes evaluation easier for you once you provide the config for the data set and the task. Because of time, I will not be able to proceed with the rest of the talk, but thank you for paying attention. Okay. All right. Okay, thank you.